Hi, welcome to this video session. Today I will talk about an interesting problem related to AES in CBC mode. Let's get straight into the problem now. The problem is asking us what can we infer about the plain text of the following two ciphertexts produced using AES CBC. Let's pay close attention to the ciphertext now. We have IV, which is initialized to 0. If we count the number of zeros, it's all in hex, by the way. You will see there are 16 bytes of zeros there. Okay. Leave that to you to count. Ciphertext 2 is also made of quite similar, but the last byte appears to be different. Instead of, as you can see, the last byte is 00 here. Here the last byte is 01. Okay, that is an interesting difference. Okay, so this is basically an important difference to highlight. Here is ending with 0, right? Here ending with 1. This part. Okay, we have more data. Next line shows the actual ciphertext itself, but let's see what's there. It looks very similar to the one above. In fact, it's the same. There's no difference whatsoever. We can quickly compare. So we are now given two ciphertexts. The IV differs from each other by only the least significant bit. If we convert this whole thing into binary, it will be, of course, bunch of zeros, 128 zeros actually. Here it will be 127 zeros and then a 1. So the least significant bit is the only difference. Okay, but the plain text happen to be the same. The ciphertext happen to be the same. We don't know whether the plain text are the same or not yet. We have to answer that question, of course. That's the question. How do we go about that part? We can try to reason about what happens if we have two ciphertexts that are produced using CBC mode. The difference between the IV is just the least significant bit, as in this case. So let's get back to the CBC mode structure. Here is the structure we already talked about in the previous segment, so I will not go through the structure again. What is interesting for us at this point is that we have the IVs that are just deferred by the least significant bit. The consequence of that is the IV of message 1, which we don't know, and the message 2, which we also don't know. They, since they are deferred by only the least significant bit, if the plain texts are the same, what can we conclude? If two plain text messages are the same, the output at this point means the output at this point. What can we say about the output at this point? The output at this point is going to be flipped. That's basically how the XOR works, right? I can write it in like a formula model. If we have, say, 2 bits X and Y, and we XOR them, okay, you get a result Z. So let me call this like this. What can we say about X XOR Y XOR 1? This must be the same as Z flipped with 1. Okay, that means if we flip a bit, let me take an example. Another example. Let's take 0001 and take 0001. What can we say about the result? The XOR in this case is 0, right? Now let's flip the this particular least significant bit of X and obtain a new X. Let's call it X2, right? Or X flipped, which is 0000, and let's keep the Y as it is. 0011. What can we say about now the new Z? Let's call it flipped Z, right? Which is 0011. Now if we compare the flipped Z with the original Z that we got before flipping, the only place they differ is the place where the bit was flipped, right? Here it was 0, here we got 1. The reason is that we flipped the corresponding bit of X. Okay, so we know the basics of how the flipping will affect the result, so I will clear this part. Okay, so now we can get back to the problem. The problem is now to reason about what can we infer about the plain text, right? That's the problem. Since we saw that the IV is just being flipped at the least significant bit, but the messages are the same. That means the ciphertext are the same. That means the message must also have been flipped at exactly the same place where the IVs are flipped, right? That's the property of how the XOR works. So I can conclude. What is my conclusion? The plain text must be different at the least significant bit only. Because, why do we say that? Because the IVs are different only at the least significant bit. Okay, and this is straightforward coming from the properties of XOR. Okay, now we can say the two messages must have got the same input to the block cipher encryption. Otherwise, they wouldn't have generated as the same ciphertext here. That's the main message, right? We got the same ciphertext for both example cases. Therefore, we must have been given the same input to the block cipher encryption. But we know IVs are different. That means the plain text must have also flipped exactly at the place. If the plain text was flipping here and IV was also flipping here, then both plain texts will have the same value at this point. Okay, the XOR of the plain text and IV would have the same value at this point. Therefore, the ciphertexts are the same. Okay, so let me walk you through the program now to confirm this is the case. Okay, we can go to the CBC counter .java program which I wrote. As we can see here, the IVs are generated in a slightly different way here. There's a method called getIV, which takes the index of the plain text and then it returns number 0 at the very first. For the first call, for the second call, IV becomes 1, so it will increment the IV by 1. That's the increment function is doing. So the IVs are basically like counters, but we can see that that's dangerous because the attacker can now infer very clearly. We can just run it for our conformance. Okay, the IVs are different, of course. Just the least significant bit is different, but the ciphertexts are the same. We can also look at the code and see that pattern is reflected here. You see here B has been replaced by C. The reason why this worked is simple. If we can go to GDB very quickly and look at the bit pattern. Oops, sorry. Wait. Clear. GDB minus quite. Print the bit pattern for say B. You can see this is the bit pattern for B and bit pattern for C. They are only differing from each other at the least significant bit. That's the reason why both the ciphertexts are the same, because the plain texts are different by the position of the least significant bit. Okay, so what is the major point of this session? The major point of the session is that we should not be using counters to generate IVs, because if the plain texts are just differing exactly at the flipped places of the IV, then we will be able to infer that what is the next plain text if you know one plain text very easily. Okay, that's basically what I wanted to show you, and thanks for watching.